Hello, hello, hello. Welcome to another exciting installment of AI for EO Platforms and Best Practices. This week is the data sources lecture. For those of you who are wondering, this is not a pre-recorded lecture from a previous semester. I re-recorded this lecture just for all of you in summer 2025. So while you're enjoying this lecture, I will be enjoying the black sand beaches of Santorini for the next week, visiting a friend for their wedding. So sorry I couldn't make it in person, but here's a lecture recording of what you missed. So like I said, this lecture is about data sources. A few administrative things. You might have noticed that on Moodle there is a new Q&A forum. So I've never tried this before, but this was requested by a student, so I figured we can give it a shot. If you have any kind of general questions that you think many students might want to know the answer to, such as, I started the homework and I didn't understand this part, can you explain it? Or I remember this topic we covered during lecture, but I didn't quite understand this lecture slide, can you explain it? Please try the new Q&A forum for those kind of questions. I can answer those questions. I think students can also answer those questions, so that will maybe save me a bit of time. For any personal questions, things like I'm going to miss lecture this week because my cat is sick, or can I get a homework deadline extension because I'm going to be out of town for a graduation ceremony? Anything like that, please email me. Email is still fine. I will still try to respond to email quickly. So that's what's new on Moodle. For homework assignments, I explained this the last couple weeks, but I'll explain it again. Every homework is released each week, and you have 2 weeks to do it. So homework 0 should be due approximately today, depending on when you're watching this lecture. So it was on Monday, or is on Monday if you're watching it before then. I don't think anyone's asked for an extension on this yet, so that will be the final deadline. Homework 1, you still have 1 more week to do it, but I'm hoping that most of you have started, and if not completely finished, are approximately close to finishing it, because homework 2 will be released today, and you should get started on that as soon as you can. In general, you have 2 weeks to do the homework, maybe a couple extra days if you need an extension, but try not to use that often. Assuming that everyone finishes homework 1 on time, I will show the solutions to homework 1 in the next lecture. Homework 0, I could show the solutions today, but there's not really any solutions for it other than for the extra credit, which I won't show. And then after you submit your assignment, I try to grade them within about a week. That might get delayed due to my vacation this time, but in general, 1 week is how long it usually takes. So these are the concepts we're going to cover today. A lot of these, for those of you who have some machine learning experience, but no experience with satellite imagery, many of these concepts may be very new to you, so I'll go through those slowly. And then the other thing I want to show you is how to actually download and visualize real satellite images. The homework assignment this week will be essentially downloading and visualizing your own satellite image, and then doing unsupervised learning on that image using k-means clustering, just like we talked about in lecture last week. So let's get started. The class is AI for EO. We explained what AI is. This week we get to explain what EO is. So when we talk about Earth observation, what we really mean is any kind of observation, any kind of gathering of information about the Earth. So examples of this can be anything from satellite imagery, weather stations and weather records, seismometers, anything where we're gathering information about the Earth. Now, there's another similar and closely related word that you'll often hear in this space, which is remote sensing. When we talk about remote sensing, we're talking about more how we gather that information instead of what we are gathering information about. So if we're doing remote sensing, we are gathering information remotely. We are gathering it without making contact with a thing we try to understand. Examples of this also include satellite imagery, but also things like ultrasound or telescopes, where we're trying to observe the inside of the human body or a distant planet or star system without actually making contact with that object. Now, in this course, almost every single lecture and homework assignment is going to be focused on the intersection of these two things. So we'll use satellite imagery, aerial, UAV imagery. You saw on homework 1 where we did actually use some weather station records, so that is another example of Earth observation. But for the purposes of this course, we'll usually be talking about satellite and drone imagery. For your final project, if you've thought about that at all, as long as you're doing some kind of Earth observation, I don't really care whether or not it's satellite imagery. So you can use weather data, you can use seismometers, you can use anything you want, as long as it is information about the Earth. Now, when we're talking about imagery, the most important thing to understand is the electromagnetic spectrum. There are a lot of different components of the electromagnetic spectrum that are worth knowing about. The sad thing is that humans can really only see a very small chunk of the electromagnetic spectrum, specifically the visible spectrum. So for this visible spectrum, right around 0.5 times 10 to the negative 6 meters, we can see basically things that are approximately the wavelength of a single celled organism. But there are many other wavelengths of light that can tell us a lot of information about different materials with different frequencies and wavelengths. So if you go for longer wavelengths, you end up down in the infrared spectrum, where you can actually see temperature as opposed to visible light. You go further and you get to the microwave spectrum, and you go even further and you get all the way down to radio waves. So you can probably tell most of these are relatively harmless to humans. Infrared light can give you a sunburn, but that's about it. You might not want to stick your head inside of a microwave, but radio waves are relatively safe and you're having them pass through your body every single day. Whereas if you go the other direction, things get a bit more dangerous. So if you go to ultraviolet, that's where sunburns get really bad. If you go to X-rays, these can see through your body. They're safe in small doses, but if you're exposed to them regularly, they can cause cancer. And then gamma rays are the most dangerous. These can actually destroy the atoms in your body if there's enough energy behind them. Luckily, the Earth's atmosphere blocks most of these, so we don't get bombarded with these very often, maybe a little bit into the ultraviolet spectrum. And similarly, many of these lower wavelength, larger wavelength parts of the electromagnetic spectrum, these are also relatively safe. They usually get blocked by the atmosphere as well, but we can emit them from our own sources and observe things using those wavelengths. The last chart on the bottom here, I think, is interesting. What a lot of people don't realize is that everything emits electromagnetic energy. So the sun happens to emit a lot of light at the visible wavelength of the visible portion of the electromagnetic spectrum. That is not an accident. Humans have evolved to see this particular wavelength of light. But that's just based on the temperature of the sun itself. Other stars will also emit light, and depending on their temperature, they will emit different colors. You yourself as a human being, you have a temperature and you emit light. It happens to be around the infrared portion of the electromagnetic spectrum. Even completely cold, dark objects that don't seem to emit any visible light still emit light at some spectrum, some wavelength of the spectrum. Now, when we talk about traditional cameras, most of the cameras that you think of that humans have been using for 100 years or 200 years, these are designed for capturing visible light. So that's the part that humans see with their eyes. Of course, that's the part that we're most interested in taking an image of. I won't go into too much detail here, but I wanted to briefly touch on the history of photography so you understand how cameras have evolved over time. The first kind of grayscale photograph, the first black and white photograph, was actually taken back in 1826. And this was a relatively primitive pinhole camera that just basically measured the amount of light passing through a small hole and onto a photoreceptor, onto a film receptor, and it would essentially burn the image into this plate. And then you could use that to print individual photos of. Now, that was the first kind of black and white photo. When we say black and white, what we actually mean is grayscale. It wasn't until 1861 where the first color photograph was created. And if you're wondering how these color photographs are created, especially in traditional cameras, what you would do is you would separate out the different wavelengths of light, and then you would capture each of those images separately onto a separate plate. So here is a really interesting image. This is not the oldest image in history, but it's from 1911, so it's quite old. And you can kind of understand how cameras work when looking at this image. You have a person sitting on a chair, and then you have 3 different grayscale images. Each of these has a different intensity. You can actually determine which one of these is red, green, or blue by looking at the combined image and understanding what bright white means versus dark black. So in this case, this first image here, you can see most of the gown that he's wearing is bright white, high intensity. That means that whatever color this originally came from, it was most reactive with this filter. So that would suggest that this is the blue channel or the blue band of the image because it's bright in the blue parts of the outfit. The second one here, it's not very easy to see. There's only a couple places that are kind of bright and they're mostly whitish. But in this second image here, or this third image, you can see that the frills on the outside of the outfit are bright. So this is likely the red part of the image, and that would make the remainder the green image. Now, when you take all 3 of these images and you stack them on top of each other, and you do a little bit of shuffling to perfectly line them up, the result is a color image. Typically, people would record red, green, and blue because those were the parts of the electromagnetic spectrum that the human eyes are most sensitive to. But you can really record any colors. It doesn't have to be within the visible spectrum. Now, that was in 1861, and it took another 100 years or so before people started taking real digital photographs. The first photograph was only, 30 by 30 pixels, a very small image. But over time, we've gotten much better digital cameras to the point where we can take images that are megapixels or even gigapixels in size. When we talk about these images, if we want to represent them in mathematical notation, we would write them as so. So you have X, that is our image. It's a capital letter because it's a matrix. It's bold because it's not a scalar. And it's within the real spectrum, so it's a real number, and it has dimension C by H by height. C is the number of channels, the number of colors, so red, green, and blue would be C equals 3, but it doesn't have to be equal to 3. In many of the images we will talk about later, C is much larger than 3. So we have a dimension for the color channel, we have a dimension for the height, and for the width of the image. These cameras can be either passive or active sensors. What I mean by that is either the light source comes from something like the sun, and you are passively measuring the light that is reflected off of an object, such as the image on the right, or it can actually be an active sensor, where you yourself are creating a light source and you are measuring the reflection of that light off of an object. And we'll see both examples of that later on. Now, in the remote sensing ecosystem in the satellite imagery space, the vast majority of sensors that we'll be working with are known as optical sensors. They work very similar to these traditional cameras. They just have additional spectral bands. So most of the satellites that we'll be dealing with capture what are called multispectral images. They do multispectral imaging. This is very similar to the RGB image we just saw before, except now we have 3 or more bands. So we might have up to 15 different spectral bands. Usually we choose the spectral bands we're interested in based on a specific application. So if we're trying to study agriculture, we know which wavelengths of the electromagnetic spectrum are most useful for understanding agriculture, and we build a sensor that is designed for those wavelengths. Usually we're talking about visible light plus infrared plus thermal, maybe even radar wavelengths of light that we're capturing. And some common examples of this include satellites like Landsat, Sentinel-2 in particular, MODIS, and WorldView. Now, the other alternative to this is hyperspectral imaging. A lot of people see multispectral and hyperspectral and they say, oh, hyperspectral is the same thing, it's just more bands. But it's actually quite different. In addition to having more bands, on the order of 150 to 250 spectral bands, we're actually talking about contiguous measurements of the electromagnetic spectrum. So here's an image demonstrating what I'm talking about. Whereas with a multispectral camera, you might have a small bandwidth that is covering the red portion of the spectrum and another bandwidth that's covering the orange portion of the spectrum, and there's a gap in the middle where we don't focus on. With a hyperspectral camera, we're actually capturing every part of the electromagnetic spectrum. There are still bars here if you looked really close, but they're touching each other and they have such a narrow width that it's kind of like if you took calculus and you remember Riemann sums, it's a very similar idea where if you have narrow enough rectangles, they basically fit a continuous curve. Another way to think about this is actually closer to something like a mass spectrometer, where you're measuring the individual components of the substance that light is reflecting off of, and you can very precisely pinpoint the type of surface or material that it's reflecting off of. Again, here examples include satellites like Hyperion, Proba. I think Prisma is an Italian satellite, EnMAP is a German satellite. So there's many different hyperspectral satellites. The resolution of these, the spatial resolution, tends to vary. So something like Landsat might be 30 meters per pixel. Sentinel-2 is up to 10 meters per pixel. MODIS is actually lower resolution, on the order of 250 meters to 1,000 meters per pixel. And then WorldView is the opposite, very high resolution. So something like 1 to 3 meters per pixel. Most of these hyperspectral satellites are on the order of 30 meters per pixel or lower. They tend to have poor spatial resolution. Now, comparing some of these multispectral satellites, you'll notice that even though you have 2 Landsat satellites, Landsat 7 and Landsat 8, or even comparing Landsat and Sentinel-2, the spectrum, the portion of the electromagnetic spectrum that these satellites capture is very different. So for example, if we look at Landsat 7, you can see there's many different spectral bands. You have 1, 2, and 3. These roughly correspond to red, green, and blue. You also have some infrared light here and here, either shortwave infrared or longwave infrared. And then you have everything down in the thermal bands as well. If you compare Landsat 7 to Landsat 8, Landsat 8 adds a couple more bands. So there's a new band 1 for ultraviolet or coastal blue aerosol is what they call it. And then there's another one out here, band 9. And all of the band numbers have shifted. So now red, green, blue is 432 in terms of band number. But each of these bands, each of these image channels will capture very different information and even have different resolutions. Looking at Landsat 8, for example, band 8 is a special band. This is known as panchromatic. This actually spans a wide swath of the electromagnetic spectrum, most of the visible light, but you get very high resolutions. You'll get 15 meters per pixel for this band 8, whereas most of the other bands, 2, 3, 4, 5, 6, 7, 10, 11, these are about 30 meters per pixel, And then once you go to bands 1 or 9, these are even lower resolution. You'll also notice on the back of this image, there's a kind of silhouette. This is the atmospheric transmissivity. So if you have light coming from the sun and it passes through the Earth's atmosphere, some wavelengths of light will transmit through the atmosphere and some will be absorbed by air, by clouds, by other materials. So some of these, such as band 9 in Landsat 8, are actually designed to focus on this band that should not pass through the electromagnetic spectrum. And this band is really only used to determine which pixels might be clouds or which pixels might be corrupted. So this is more of a quality assurance kind of thing. So there's many different types of multispectral imaging sensors. You can see Aster and MODIS are also on this list, but most of them tend to capture the same things: the visible light, near-infrared light, shortwave infrared, long-wave infrared, and thermal energy. When we go to our hyperspectral data, we're actually talking about more of a three-dimensional hyperspectral data cube. So instead of having an image that's height by width, we also have a new dimension for our color channel, our wavelength. So you can see some examples here. This is what I mean when I say it's kind of like a mass spectrometer. You have different components of the spectrum that measure different things. So if you look at the cross-section of a particular land surface, you get something like a digital fingerprint for that particular material, where different species of vegetation will have very unique fingerprints. Different types of soil with different moisture contents will have different fingerprints. Different man-made materials, different roofing materials will have slightly different digital signatures captured by this hyperspectral image. There's generally a trade-off between these different sensors. So the more spectral resolution you have, the more bands of the electromagnetic spectrum you are measuring, that typically results in a lower spatial resolution. So these bands are very narrow. There's very few photons of light that are traveling per a particular band. So you need a larger pixel size to compensate for that in order to avoid noise. Another type of sensor that I want to talk about that is not an optical sensor would be something like radar. So there are many different types of radar instruments. Radar itself stands for radio detection and ranging, but it turns out that radar actually does not use radio waves, it uses microwaves. Now, radar was originally discovered and used for meteorology applications. You can fire something like Doppler weather radar and measure the time that it takes a signal to bounce off of a group of clouds and return back to the receiver, and then you can tell where and how large different storm cells might be. You can measure things like precipitation, clouds, even wind speed using these sensors. This is not the only application of radar. Another one that happens to be useful for Earth observation is known as ground penetrating radar. In the exact same way, you can fire a small seismic pulse down into the ground and measure the time it takes for that signal to reflect off of materials buried underground, including things like bunkers or ancient buildings, or also oil reserves. Now, there's an extension of radar known as synthetic aperture radar. When we looked at the electromagnetic spectrum for radio and microwaves, you notice that the wavelength of this light is very large. And as a result, you actually can't measure small changes in a surface. So what you can do is you can make your radar receiver, your radar antenna, larger. And if you make it larger, it can capture detail at a much finer resolution. The problem is there's a physical limit to how large you can make a sensor, but what you can do is you can actually move the sensor. And if you take measurements at multiple different locations, then you can get a much higher resolution image. You can do that by having multiple sensors. So maybe you have several different antennas in a large array or grid. But what we do oftentimes in Earth observation is we put that radar sensor on a satellite and we fly that satellite around the Earth. And that effectively increases the aperture of the sensor, synthetic aperture radar. Now that we have finer resolution, finer detail, we can make very precise measurements of things like elevation. So you can build a digital elevation model of topography. You can measure things like flooding. You can even use this for glaciology and peek into the surface level of the ice and snow in order to understand how thick the ice is on a glacier. Now, another trick that scientists have invented over the years is an extension of this. It's called interferometric synthetic aperture radar, or INSAR. And this is a really interesting example because what you're doing is you're taking a synthetic aperture radar image and you're taking another image at a different time. Now, these images are really interesting because they're not simply floating point numbers. They're not simply a amount of light, an amount of photons that are being captured. Because these sensors use an active light source, we're not taking microwaves from the sun, we're taking microwaves from the satellite itself. Because we're using an active light source, we can measure the time it takes for that light source to bounce off the ground and reflect it and return back to the original satellite. So this active signal is really nice because you can make your satellite work at night. So you don't need to rely on the sun. It works 24/7. And also, these microwaves pass through clouds. So even if there are clouds overhead, you can still see the surface of the Earth using microwaves instead of visible light. So the idea with INSAR is we take two images at two different times. Instead of only capturing the amount of light that's returned, we also capture the phase of light. So we fire a polarized light source at the ground and we measure the phase that's returned. This is a complex number, so we have both an amplitude and a phase. And by comparing the phase of two different images at two different times, you can get an image like on the right. Now, what this image is capturing is this is a location where there was an earthquake. And these little bullseye patterns you see are regions of subsidence, where the ground moved down a little bit, or uplifting, where the ground rose a little bit. By a little bit, I'm talking on the order of millimeters. So you can measure very small changes in the surface of the Earth due to things like earthquakes, due to groundwater being depleted, or also due to volcanoes such as the ones on Santorini rising up over time as the magma chamber fills. All of these things can be really useful for predicting volcanic eruptions or measuring groundwater reserves. Again, I mentioned this already. This is an active sensor, so it works at night. We don't need to wait for the sun to illuminate the Earth. We can fire a polarized light down to the Earth, and it will penetrate our clouds for us, and it works all year round. The downside of this is that it's a little bit trickier to work with complex numbers, and it's a little bit trickier to analyze this data, but there's a lot of advantages to working with SAR and INSAR data. We won't cover this data too much in this class, but if you find this interesting, this could be a good topic to dig deeper in for your final project. Now, similar to radar, you can do a very similar idea with lasers. So if you use a laser, there's an application called LiDAR, which stands for light detection and ranging. It's similar to radar in some ways. It's an active sensor. You are firing a laser at the ground, so it's going to work at night. But it's also very different. Usually the light that we're using is something like an ultraviolet, visible, or even infrared laser, and the image that it's capturing is actually a point cloud, not a kind of raster image where every pixel has a value. So here's an example of what this looks like. You can fly a drone over a forest, and you can have a moving laser that scans the ground, and you can build these three-dimensional point clouds of places, trees, branches, or even ground surface where that laser has been reflected off of. Then you can take that three-dimensional point cloud and you can try to build a 3D model of a forest, of buildings, of whatever you're trying to study. There's a lot of different applications here, just like most of these other sensors. These were originally invented for things in meteorology, studying clouds and aerosols in the atmosphere. You can also use them for things in geodesy if you want to do surveying, or even archaeology, where you fly one of these sensors over a forest and you find buildings that are hidden behind trees. They also have a lot of applications in forestry if you're trying to measure the height of trees or even the total mass of trees to understand how much CO2 those trees might be sequestering. Now let's talk about the satellites. So if we have a satellite, what are some ways that we can fly a satellite? If you're in aerospace, maybe this is something you know even better than me. So there's many different types of satellite orbits that a satellite can be in. The simplest would be something like, I guess not simplest, but the first one I will start with would be a geosynchronous orbit. So imagine a satellite that always has the same longitude as Munich. No matter what time of day it is, it's always above Munich. But it might not be perfectly above Munich. It might be north or south of here, but somewhere on that latitudinal line. As the Earth rotates, the satellite revolves around the Earth, but it's revolving around the Earth at the exact same speed that the Earth is rotating, allowing it to essentially hover in place. A subset of a geosynchronous orbit would be a geostationary orbit, and this is where it's hovering directly at the equator, and therefore it's essentially hovering at the exact same place at all time, day and night. It's hovering, but it's actually revolving around the Earth, so you don't have to worry about gravity pulling it down to the Earth. What does this look like? Here's a nice GIF that illustrates this. You can see it's somewhere above Ecuador, maybe, and it's revolving around the Earth at the exact same speed that the Earth is rotating. You'll notice that the Earth is on a slight axis, 23.5 degrees with respect to the sun, and maybe the sun is somewhere on the left, and it's hitting different points of the surface at different times of day. So this is known as a geostationary or geosynchronous orbit. This is common for weather satellites, for communication satellites, where you basically want continuous coverage for one place. And then you can launch several of these satellites so that the GPS network stays active in place, so that weather satellites are always looking out for hurricanes and other storm systems over time. In Earth observation, when we're actually studying the surface of the Earth, instead we typically use what's known as a sun-synchronous orbit. Again, there's a couple different types of these. The simplest is known as a polar orbit. So a polar orbit just means that it's essentially revolving around the Earth's poles. It's going up and down, north to south, south to north, rotating, revolving around the Earth as the Earth rotates. A subset of this polar orbit is known as a sun-synchronous orbit, where the alignment of the satellite just so happens to be perfectly aligned with the sun. So essentially, the satellite is always looking at the Earth at solar noon or solar midnight. It's actually not exactly solar noon. It's actually more like 10:30 a.m. because if the sun is directly behind you, then you're going to get reflections off of water that will mess up the sensors. So it's shifted a little bit, but it takes an image of the Earth at the exact same time of day all year round. So you get consistent imagery of the Earth, and it's easy to interpret this imagery. Here's an image, a GIF, illustrating this. So you've got a satellite that's revolving around the Earth, pointed at the ground, and it's capturing an image of the Earth at the exact same time every day. Typically, these overlap with the same location on Earth anywhere from every 2 days to every 2 weeks. It depends on how large the area of the surface of the Earth it's covering. So you can kind of think of that as the temporal resolution of the satellite, the repeat period of the satellite. How long do you need to wait for this image of Abu Dhabi to be taken again by the same satellite? For something like Landsat, it's about 2 weeks. For Sentinel-2, it's about 10 days. It just depends on the satellite. the speed of the orbit, and the size of the image. Now, we've talked about a lot of different sensors, especially optical sensors. And I just mentioned, oh, there's Landsat, there's Sentinel, there's all these different sensors you should know about. So a question at this point might be, how do we choose the right sensor? If there's all these different satellites and sensors out there, how do I pick one that's useful for what I'm trying to study? And typically it boils down to having the right resolution. So there's many different resolutions we might be talking about. Usually people think of the spatial resolution of the image. And this is actually a little bit tricky because in computer science and computer vision, the resolution of the image is the number of pixels, the height and the width of the image. Whereas in Earth observation and remote sensing, when we're talking about spatial resolution, we're usually talking about ground sample distance. What is the size of 1 pixel in meters on the actual surface of the Earth? So the spatial resolution, whenever I use resolution in this course, it will typically mean ground sample distance, unless I specify otherwise. Again, there's many different resolutions out there. If you're looking at weather satellites like GOES, they could be relatively low resolution, 4 kilometers per pixel. If you're dealing with expensive commercial satellites like Maxar, these can get down to as high as 30 centimeter per pixel resolution. So you can see very small objects, even cars, ships, probably not on the order of people, but if you have a top secret military satellite, maybe those would get even higher resolution. And then if you fly a drone or UAV low enough, you can essentially get whatever resolution you want. So typically something on the order of 7 millimeters per pixel, depending on how high or low you fly the drone. In addition to spatial resolution, you can also talk about the temporal resolution. That's the repeat period that we talked about. This could be continuous for a geostationary satellite, or it could be something like daily, weekly for one of these sun-synchronous polar orbit satellites. And if it's something that's captured by a plane, it might be something that's only updated once per year or never updated. We just have a single static image of the Earth taken at one time. That's all you get. There's no temporal resolution. So depending on what temporal resolution and what spatial resolution you need to study a particular Earth phenomenon, this is how you would choose your sensor. And then the third type of resolution is the spectral resolution. This is the number of spectral bands or channels, or the bandwidth of each of these spectral bands. So it can be anything from a grayscale or panchromatic sensor, where it's only capturing one spectral resolution, but it's very high resolution, to something like a hyperspectral image where there's hundreds of spectral bands at a relatively lower spatial and temporal resolution. Okay, so now that we've finished the concepts, let's talk about downloading and using imagery. Most of the imagery we've talked about so far is actually free to use and available through various free services, especially many of these multispectral satellites that you see here. Some of the other sensors that we discussed, such as Digital Globe Worldview or Maxar, those are paid, so you don't generally have free access to those, but we'll talk about the freely available ones. You'll be downloading one of these images for your homework assignment for multiple weeks during the course, and then you'll also be likely using some of these data sources on your final project. So this is a really good time to pay attention. Let's start with Landsat imagery. So I'll talk about the Landsat system, the Landsat constellation collection of satellites. There's actually been 9 Landsat missions in total. It's the longest running Earth observation program in history. It's been running since July of 1972 and provides more or less continuous imagery of the Earth from 1972 until today. It's a little bit lower resolution for older satellites, maybe 60 meters per pixel. For newer satellites, more like 30 meters per pixel. But it has such a long time history that it allows you to study very long-term changes of the Earth's surface on the order of decades, which is what we care about if we're doing any kind of climate change study. You'll notice that not all these sensors have the same lifespan, so many of these satellites died early. Landsat 6 in particular failed to reach orbit and crashed back down to Earth, so its lifespan is only a few days. Whereas Landsat 5, before it, and Landsat 7 have an extremely long lifespan, much longer than the creators actually thought the satellite would last. Any of these cross-hatched regions, such as Landsat 7 here, anything after this particular date, around 2007, there's partial or complete sensor failure in these regions. So in the case of Landsat 7, there's something called a scanline corrector that controls basically the position of the camera. That broke, so you get these weird images that have stripes. But the stripes that have data are still very useful. So the satellite is still flying and they're still collecting information about that satellite mission. Here are the exact same satellites again. This is interesting because different satellites actually carry one or more sensors on board. So for example, Landsats 1 through 3 carried two different sensors, the return beam Vidicon, which was kind of like a regular RGB camera, and also the multispectral scanner, which was more of a multispectral imaging source. It turned out when they launched Landsat 1, the return beam Vidicon broke almost immediately. So actually the multispectral scanner, which was originally added as a backup camera, became the primary camera and turned out to be extremely useful. They kept it around for 5 generations of Landsat. In Landsat 4, they ditched the return beam Vidicon and replaced it with the thematic mapper. In Landsat 6, they had an enhanced version, but that satellite crashed. So then in Landsat 7, they had Enhanced Plus, an even better one with higher resolution. And then with Landsats 8 and 9, there's two different sensors, one for optical imagery and one for thermal infrared imagery. And then Landsat 10, which will be the next generation, is named Landsat Next. It will be released and launched in a few years, I think, but it will have significantly more spectral bands to match Sentinel-2 at much higher resolution to match Sentinel-2. So that's coming soon in the future. Look forward to that. Again, different Landsat missions have different spectral bands. Here's the Landsat Next sensor I talked about earlier. So you can see it has many bands at 10 meter resolution, many at 20 meter resolution, and some at 60 meter resolution. And it will have up to 26 bands, not just the 10 or 11 of previous editions of Landsat. And again, these are typically lined up with the atmospheric transmissivity or with previous sensors where we think that these specific wavelengths happen to be useful for common applications in Earth observation. The other thing to be aware of is the product level of the image you download. So every image recorded by a satellite goes through many levels of processing before it comes to the user. The first image that the satellite or sensor takes is known as a raw image or a level 0 image. So you can download this raw product. It's just not very useful because it hasn't been aligned somewhere on the Earth. You have telemetry data from the satellite, so you know approximately where the satellite was and approximately what angle the satellite was pointing at. So you can guess where it was on the Earth, plus or minus a kilometer. This is still useful, especially if you're studying a natural disaster that just happened a few hours ago or a few days ago. You want that image as soon as possible so that you can study what damage was done to the Earth and do disaster relief and aid for people who are impacted by a natural disaster or a war or anything like that. But typically, unless you're doing those immediate response applications, you typically wait for a level 1 or level 2 product. Level 1 is known as TOA, or top of atmosphere. This is an image that has been geometrically corrected and projected onto a digital elevation model. It has been very precisely geolocated to a single location on Earth. But there's still a lot of noise in the image. There's still atmospheric effects that can corrupt the image and change the colors of the pixels in the image. If you ever looked at the Earth while you're on a plane, you'll notice that the Earth kind of has a little tinge to it. So this is what a top of atmosphere image would look like. You can see the image on the right. The top of atmosphere has a little bit of a blue tinge to it compared to the surface reflectance product. The surface reflectance product has a bunch of additional pre-processing steps that include atmospheric correction. They try to remove the effect of really thin clouds or atmospheric particles and are really useful for surface applications. But if you're studying the atmosphere itself, either studying it for meteorology or studying it for air pollution, you would rather use the top of atmosphere image. So typically in this course, almost everything that we will do will be either surface reflectance or top of atmosphere. And then finally, there's level 3 products as well. These are so-called derived products, things like dynamic surface water maps, fractional snow cover maps, burned area maps. These are basically classified images created from satellite imagery that are also released by the same people who release the other products. We'll talk a bit about the pre-processing steps that go from level 0 to level 2 in 2 lectures in the pre-processing lecture. For now, all you really need to care about is TOA and surface reflectance. You don't really need to think about any of the other options. There's another thing that's useful, especially for the Landsat system. So when you have this satellite revolving around the Earth is also rotating at the same time. And as a result, you get these kind of diagonal trajectories where the satellite one day will be passing down path 26 and it will capture images one after another. And then maybe the next day it will be traveling down path 29 and it will cover these areas. And then a couple days later, it will be covering path 32 and it will cover these regions. And then at some point it will cycle back around and cover the missing gaps in the middle. So you'll notice that some locations here where there's overlap between 2 images, you can actually get coverage up to 4 times during that 2-week period, whereas other locations nearby will only get coverage once every 2 weeks. It really just depends on where you're located, how far you are from the equator. That really governs how much overlap there will be for different images. But this is the path that Landsat happens to take. And so when you download images, you can actually say, I'm looking at a specific location of the Earth in Texas, specifically path 30, row 38, or maybe some adjacent rows or paths. So you can also locate your images using this system. So the first place that I want to teach you where to find and download images is from the USGS, the United States Geological Survey. They host a website known as Earth Explorer. I'll show you the website here on my screen. Hopefully you're able to see this. So this is USGS Earth Explorer. There's the URL. You can make an account for this website if you don't already have one. I've already made one. It just asks you simple questions like, where do you work, aka TOMB? What kind of data do you use, or what kind of things are you studying? You can put in a generic response like education or whatever. But make an account for this website, and that will allow you to actually download imagery. Now, there's several different tabs up here. These tell you how to narrow down your search constraints. So what we're going to do is we're going to pick an interesting location and we're going to find an image. By interesting location, I mean it shouldn't just be an image of the middle of the ocean where everything is blue. It shouldn't be a forest where every pixel is green. It should be somewhere that's a little bit diverse. So I'll zoom out a bit and I will look at Greenland, the so-called 51st state of the US that Trump is trying to steal right now. And I'll go up in this region where we can see some really interesting glaciers. So if you zoom in far enough, you can actually see individual crevasses in the glacier. This is a real satellite image of this glacier. I'll zoom out a little bit and I'll find an image somewhere in this region. You can see there's many different glaciers in this region of Greenland. So maybe I'm a glaciology researcher studying this particular region. There's many different ways that you can narrow down your search constraints. So for example, if you're in the US, you can say, I'm looking for a particular state, or I'm looking for a particular county. Maybe I want to specify a polygon where I draw different pixels on the map and say anything within these bounds. I can actually specify a circle, a particular latitude and longitude and radius. I can upload a GeoJSON shape and sample things from that. What I'm actually going to do is I'm going to use the map viewer in my image. So I've zoomed into this particular location. You can see the latitude and longitude in the upper right corner. If I click Use Map, it will select this portion of the map. It will create a little polygon for me with 4 points. I can even download this polygon if I want to. I can clear this and do it again, or I can actually add multiple polygons. So I've specified my location. The next thing I might want to specify is a date range. In particular for places like Greenland, it's kind of hard to see these places in the winter. There's a lot of clouds in the winter. Maybe everything is buried in snow and everything just looks white. So I will pick a date that's kind of in the summer. I will look at the previous year, and I'll go from April 2024 to, did that work? I don't think it did. Let me try again. April 2024, I'll pick a particular day, and then I'll go to the end of the summer last year. So maybe September 2024, the end of the month. I can also specify individual months if I want. That's another way that I can narrow it down. So now I've narrowed down the location and the time. I can also specify what level of cloud cover I'm willing to accept. So an image that's 100% clouds, I'm not going to see anything on the ground. That's not very useful. 0% is relatively uncommon. I want to maximize my chances of getting a good image of this glacier. So let's say 0 to 20% is a good option. How many options do I want? 10 per page. That's fine for now. I don't care too much. So now I've specified some of the criteria that I want to look for. The next thing I'll do is I'll go to the next tab, Datasets, and I will specify what images I would like to look for. You can see NASA and the USGS offer a lot of different satellite images you can download, including radar data, vegetation monitoring, even commercial satellites that have been released publicly for free. I'm specifically looking at Landsat. There's many different collection levels that you can choose from. I'm interested in that level 2 data. That's the surface reflectance data. And I'm interested in Landsat 8 or 9. That seems fine. So I've selected level 2, Landsat 8. I can go to the next tab, which is additional criteria. So there's other things that I can specify here. If you know the name of the file you want to download, you can actually specify the name here. If you know the WRS path or row, which we talked about on the previous slide, you can specify that here and say, I want to download data from this particular location. For satellite, I can say I want either Landsat 8 or 9. So let's say Landsat 9. It's newer. Maybe the data is slightly higher quality. Different sensor identifiers. So you can specify whether you only care about the optical images or also the thermal images. I don't care. Anything you can give me is great. Collection categories. You can get different quality levels. So real time is that data that's really not been geolocated properly. Tier 2, they tried to geolocate it, but it didn't work very well, but you can still download the image. Tier 1 has been very well geolocated. Every pixel lines up exactly on the Earth. It's in the right location. It's much more useful for time series analysis. I don't care. I'm just going to download a nice looking image. And then I can finally move to the last page, which is the results page. It will search the database and it will find images of this particular region. So this one looks pretty good. I can click on the image and see what it looks like. It covers this whole area. You can see there's some thin cloud cover on the eastern side of this image, but the rest of the image is quite clear. We can see the glaciers we're interested in very clearly. Here are the product identifiers, the date that the image was taken, collection category, tier 1, collection 2, level 2 image, the WRS path and row, all the other metadata about the image when it was recorded, location, etc. So this is all useful metadata. I can close this image. There's a few different options I can see here. So this first one actually draws a little bounding box where you can see the footprint of the image. This is where the image was located. It's actually only partially overlapping with my region. So if I'm studying this specific glacier, it doesn't have coverage. But if I'm studying these glaciers down here, it works fine. So we'll move down here. We can also put a RGB overlay on top of the image so you can see what the image looks like when it's placed on the map. There's other buttons we can look at here. Does it tell me what this does? Compare browse. So if I want to compare multiple, I can, but I don't care about that for now. Show metadata and browse. We've already seen this. This is what happens when you click on the image. These are the last two options that we care about. So we can either download this image or we can add it to a list. We can add it to our shopping cart. We can add several images to our shopping cart. We can have the USGS prepare those images for us and send us an email link where we can download all of those images at the same time. So if you're doing a bulk download of multiple images, you can think of that very similar to a shopping cart. We actually just want a single image. We don't care that much about how quickly it takes to download. We just want one image right now. So we'll click this download option and we'll see what's available. There's two options. They're both surface reflectance. One has 13 files, one has 14. The first one is for surface reflectance, so that's the optical image. That's from the OLI sensor. This is the one we care about. There's also a surface temperature one. This is for the thermal infrared scanner, the TIRS sensor. We're not going to be using that for the homework assignment this week. So we can either add them to our shopping cart like we talked about before, download all of the files now, which is what we're going to do, or we can select individual files if we don't want all of them. We'll be looking at these SR files. You'll notice there's other things here as well. There's these QA bands. This stands for quality assurance. So if you want to know which pixels of the image are most likely to be clouds or most likely to be partial clouds, these QA bands will tell you. Some of these other things are just metadata and telemetry from the satellite. These may or may not be useful to you. It's really these SR bands that we care about most. But we'll download all of these 13 files, and this may take a while, but it should download them all for you. It seems like it's actually only downloaded one. There's a little pop-up here. We will always allow pop-ups. Done. And if we do that and download again, it should actually download all 13 files. So you'll notice that it's opening a new window for every file that it's downloading, and it's downloading all of these files at the exact same time. This will take a while, so we'll come back to this later. So this is Earth Explorer. This is what you'll be using for your homework assignment this week. There's many other ones that we care about. So let me go back to the slides again. NASA also has many websites where you can download data from their missions. So I'll quickly show the websites for these, but won't spend too much time on this. Here's the Earth Data website hosted by NASA. Again, you can search for specific data sets, data catalogs. They have 110 petabytes of data, so about as much data as you could possibly want. You can browse by specific topic. Maybe you're studying glaciology, maybe you're studying the solid Earth or the ocean. All my data is finished downloading, great. Let me close this, okay. So depending on what thing you're studying, you can find data for different things, not just Earth observation data, not just satellite imagery, but also things like oceanic data. They have a lot of really interesting data sets here. Let's look at this. Yep, there's things for chlorophyll, there's things for lagoons, there's things for sea ice. Really depends on what you're studying. So also, when it comes time to work on your final project, the main question I want to know up front is what data is available. You will and should go to websites like this and look for data. So I showed you Earth Explorer, I showed you Earth Data. The other one that NASA has is NASA's Open Data Portal. So they have a data catalog where you can find additional data sets that are redistributed by NASA. Don't ask me why they have two websites. That's just how things are in the US. Maybe all of them will disappear in the next few years with the Trump presidency. Who knows? And also, all of these websites are always very slow. So enjoy that while it lasts. Hopefully everything will be fine when you download imagery for your homework assignment. Yep, you can see many different types of data sets, everything from atmospheric data to earth science data, from NASA, from all of these other different agencies within the US government where you can find all of their data free and easy to access. Okay. So that was, let me go back a few slides, that was NASA. The other thing worth knowing about that you will likely use in this course is Sentinel, especially Sentinel-2. We've already seen this image before. Sentinel-2 has a lot more spectral bands than Landsat. It's got 12 instead of 10 or 11, depending on which generation you're using. And they tend to have higher resolution, all the way down to 10 meters per pixel for some of the RGB and near-infrared bands, which we use most often. There are also 20-meter resolution bands and 60-meter resolution bands. It just depends on what image you're looking at. So this is the data available for Sentinel-2. On the extra credit for this homework assignment, and in the homework assignment in 2 weeks, you can use Sentinel data. So it's also worth knowing how to download Sentinel data. You can download it from the European Space Agency. Again, there's a couple different websites that you can view. Let me show you what these look like so that you know how to download Sentinel data. So we have this website. This is just the generic EO gateway. You can see many different satellite missions that are available from ESA and how to download data from those. We're specifically looking at the Copernicus program, which is the name for all of the Sentinel-2 constellation of satellites, Sentinel-1, Sentinel-2, etc. They have a DataSpace website where you can actually browse the data available and download it directly. So I will go to this data browser. I will log in. Again, if I want to download data, I usually have to log in. Just make a quick account. It shouldn't take very long, and it should be approved pretty quickly. Again, I can download data for anywhere I want in the Earth. Usually they don't record images of the ocean because it always looks the same, but they have very good coverage of most of the world in many different regions around the world. So let's say I'm specifically interested in Tierra del Fuego down in Patagonia, in Argentina, or in Chile. And I can also study glaciers way down here. There's plenty of mountain glaciers that feed into the ocean down here. So let's find a particular image. You can see the base map is not always pretty. Sometimes there's cloud cover that makes it difficult to see these things. I can use many of the same search criteria that I would use on Earth Explorer. It's just a different interface. So for example, I can select a single date. I can select a mosaic of imagery. So this is the best image for the whole year at a given location. Or I can also have a time range anywhere between certain months. So I will pick a time range like I did before, and I will say, again, April 2024, anywhere from April 1st to the same end of September in 2024. you'll notice that these little pixels that are available for clicking, these are days where there is an actual image recorded by the satellite. Notice that the satellite does not occur over a specific region every single day. So now we have some image from this time span. Cloud cover percentage, let's say less than 20% again. That seemed to work quite well last time. Okay. Mosaicing order, I don't think that matters to us. Now, there's many different layers that we can visualize. Right now, we're looking at the true color image, the RGB visible light image. You can also look at things like a false color image from bands 8, 4, and 3. Optimized natural color NDVI we'll talk about in a couple of weeks. SWIR we'll talk about in a couple of weeks. But for now, true color is most useful. Okay. So now we've picked some random image in this time range. Actually, let's go back and look at a single image and select the one that's most useful to us. So again, we'll go to the middle of the year in 2024, and we can pick individual days and see what our available image looks like. So this image doesn't look great. We can't really see anything in this image. Let's go to the next one. Again, there's quite a lot of cloud cover in this one, so that's not too useful. We can keep flipping through this until we find an image that's relatively clear. There's one problem that I should have realized when I looked at this earlier. I'm looking at July, which is the summer, but I'm in the southern hemisphere. So this is the winter, and that's why our images are very unclear, very covered in ice, a lot of cloud cover. So let's actually go to a different time of year. Let's go to January and see what the images look like in January. Now we can see much more clearly. There's a lot of clouds, but we don't have to worry about snow or ice. Now you can see there's several glaciers in this region that are feeding into this particular location. Okay, so we visualized our data. We can also search for a particular data source. We're interested in Sentinel-2. We're interested in level 2A, just like we were with Landsat. This is the surface reflectance. We're interested in less than 20%. We can again choose the time range, and we can find search results. There's only a couple images during this search range, so maybe we would have to specify a longer time range. Again, let's choose somewhere around the winter months. That will be much easier. That did not work. I need to pick a day. Yep. And then maybe the end of this month or beginning of February. Sure. Let's search again. So now we're looking at the Southern Hemisphere summer in this region of Tierra del Fuego. No products found. That is not good. Why not? Is my cloud percent too low? Let's try again with 40%. Let's try the year before. Maybe they're just not available yet. 2024. I did not click a date first. To the end of February 2024. Search again. Okay, there's one image available. Let's take a look at it. This looks perfect. This is exactly what we like to see. We can look at the different false color images. Different images will highlight different features. These are the layers view, highlights panel, compare panel, pins panel. So many of the same things we saw earlier. This is Sentinel-2 level 1A. These are all the layers we can choose from. And then if we want to download this image, we find products for current view. This is our image we selected. Again, we can look at the metadata for this image, just like we did in Earth Explorer. Find more information about the product, exactly the millisecond that the image was taken on, and also when it was processed by the facility. We can see information about the image, multispectral imager, Sentinel-2, Sentinel-2A specifically. There's 2 satellites, Sentinel-2A and B, and we can download individual files of this image. We're actually going to download all of them. So we can click this download link, and it should be downloading the entire level 2 Sentinel-2A image for this location. So while that's running, I'll go back to the slides. Okay, so we've downloaded a Landsat image and a Sentinel-2 image. There are many other data sources available, especially in the cloud computing world. So things like Google Earth Engine, Microsoft's Planetary Computer, or Earth on AWS are also really good places to look for data sets. We have an entire lecture on cloud computing, so I'll come back to these later. We'll discuss these in 3 or 4 weeks, and I'll show you some of the data sets that are available on these places and how to download those. For now, we will stick to these original data providers like NASA, ESA, USGS. Okay, so we have our images. The next thing we might want to do is visualize this data. What does this data look like? How do I load these images? What file formats do they use? How can I load these and manipulate the data and study the data? So there's a couple tools that you should be aware of in order to use this data. The core of the entire I/O system for geospatial data is called GDAL, the Geospatial Data Abstraction Library. You will be using this very heavily in this course, but only indirectly. So you can use GDAL itself, which is a C++ tool, or you can use a library like Raster.io or Fiona. These are Python libraries that wrap around the C++ bindings so that you can write code in Python and use this very fast GDAL library to do things like reading data or manipulating data, reprojecting data. I'm going to talk about GDAL and Raster.io in a lot of detail in the pre-processing lecture in 2 weeks. For now, I'll just show you a couple quick commands that you can use. So if I go back to my terminal, I assume most of you have little to no experience with the terminal. On Mac OS, it is this cute little terminal application. Mine is pinned, but if you don't know where it is, you can hit Command Space to go to the spotlight, and you can search for terminal, and you can open up a new terminal. If you are on Linux, you already know what a terminal is and you use it every day. If you are on Windows, there are like 20 different terminals to choose from and you have to pick one. I would personally recommend the Windows subsystem for Linux that I talked about earlier because it is designed to emulate the exact same terminal experience from Mac and Linux. I will only show you a couple of commands that you can use, but I highly, highly recommend learning to use the command line and learning to use the terminal. There are a couple really good free books that I shared in Lecture 0 for learning the Linux command line. So let's say you are on Mac or Linux and you have your terminal open, or you are on Windows and you installed this Windows subsystem for Linux and you have a fake Linux terminal on your Windows computer. When you first launch it, you will be in your home directory. If I type pwd, I will see I am in /users/atom. That is my current directory, that is my current folder. If I do ls, I will see all of the files and folders in my home directory, including my documents folder. The data that I'm specifically interested in is in the documents folder. So I can type doc, I can hit tab and it will complete it for me. I don't need to type the whole thing. I can see all of my folders and I can keep typing out until I get to the exact directory where I downloaded my data to. Typically this will be in your downloads folder. I actually moved it to my course folder earlier, just in case it didn't download correctly, and I can use cd to change directory. So now I am in this folder with a bunch of other folders. There's one for Landsat, there's one for Sentinel. So I'll go to my Landsat folder. Again, I'll use ls to see a list of all files in this directory in this folder. So these are all the files I downloaded. And there's a couple different commands that I can run to investigate these files. If I have GDAL installed, there is a GDAL command called GDAL info. For those of you who do not have GDAL installed, if you run GDAL info -- help and it says, I've never heard of this before, it's not installed, you can install it. The easiest way to install it is with Conda. You can maybe install it with pip, but it usually doesn't work very well, so I would recommend Conda in this case. If you did the extra credit for Homework 0, you already know how to install GDAL from source. Hopefully you usually don't have to do that. Usually installing it with Conda or Homebrew or whatever is much easier. So if you have GDAL installed, you can run GDAL info and you can give it a specific file name. So I will specifically look at this file. You can see the file name Landsat 9. This is the path and row. This is the date that the image was taken on and the date the image was processed on. It is a level 2, tier 1 surface reflectance band 1 image. If you remember, band 1 for Landsat 9 is actually that coastal aerosol band, whereas band 2, 3, and 4 are the blue, green, and red bands. So I will run GDAL info on this specific file, and it will spit out a lot of information about this file. It is a .tif file. The driver is GeoTIFF. So this is kind of similar to TIFF files, which are commonly used for images, except it has geospatial metadata embedded in the file format. If I tried to load this image with macOS Preview or Windows Image Viewer or whatever it's called, it's not going to work because it doesn't know how to view a GeoTIFF file. So we will use special tools like GDAL and GIS to visualize this file. Okay, so we have our file. This is the file name. This is the size of the file in pixels. So it's almost 9,000 by 9,000 pixels. It's a very large file. There is a coordinate reference system of the file. I haven't really explained what this is yet, but I'll talk about this more in the pre-processing lecture. You can think of this as a way of referencing the file somewhere on Earth. This is the origin of the file in this coordinate reference system measured in meters. And each pixel is 30 meters by 30 meters. The file is compressed and there's an interleave. I'll talk about these things more in the pre-processing lecture. Don't worry about these for now. These are the coordinates of the file in both meters in this CRS and also in latitude and longitude. There is one single band in this file, and each pixel is uint16, which means that the values in the file range from 0 to 2 to the 16 minus 1. Those are the range of values that every pixel can take. Okay. If you don't have GDAL installed, or installing GDAL is too much of a pain, Raster.io is much easier to install, and some of this same metadata can be got using the Rio command. So Rio is a command that you get when you install Raster.io with pip or Conda. I can look at all of the options available using --help with 2 dashes. There's many different commands here, including an info command. So if I do Raster.io or Rio info and give it the same file name, I can get a lot of interesting metadata about this file, including the block size, which we saw right here. I can get the bounds, the meters UTM zone bounds, color scale, compression, number of spectral bands, coordinate reference system. The driver is GeoTIFF, uint16, Height and width is somewhere down here. Resolution, shape, transform, etc. So all of the metadata I might want about this file. You can also get this directly in Raster.io by opening the file and querying the metadata, and then you can use it in Python more easily. So these are the two commands that you can use to gain info about the file. You'll notice that there are many files here for many different color channels. For homework 2, we are specifically interested in the red, green, and blue bands, which are bands 4, 3, and 2. So we would like to take these bands and combine them into a single file so that they are more easy to view in a GIS tool. I can do this in Raster.io, and it takes 10 or 15 lines of code, or I can do this on the command line with one line of code. Again, there's a command for GDAL and a command for Rio. So with GDAL, I can use a command called GDAL merge. I specify -separate with only one dash, and that means that I have many different spectral bands and I want to combine them into a single file. I don't want to merge multiple images into one mosaic. I want to stack them along the channel dimension. So -separate means do that. -o is the name of the output file, and then I specify all of my input files. I can either specify this file name, followed by this file name, followed by this file name, band 4, 3, and 2, or I can do a quick bash trick where I can say, give me these files, this number varies from 4 to 2, both of these are equivalent. I'll show you the other because it's a little bit simpler and easier to understand, but that would be equivalent to doing 4, 3, 2. And I can run this command and it will create a new file for me with this name. So now instead of band 1 or band 2, it's going to be GDAL. I created this file using GDAL. This is a merged RGB band. You can name it RGB if you want. This command should be very quick. A couple semesters ago, I had a student who ran this, and he said that it took him like 3 hours and created like hundreds of gigabytes of data that filled up his entire computer. If this takes more than a few seconds to run, you're probably doing something wrong. So this should be very quick. There are in fact ways to make it even faster if you read the documentation for this. Now again, there's an exact same command for Raster.io. You can do Rio, I think it was Rio stack, and the exact same thing, the output name and the bands that we would like to stack together. I can run that same command. In this case, I already have a file with that same name that exists, so I'll delete it and run it again. And it should be very quick. It should not take more than a few seconds. If it takes more than a few seconds, you did something wrong. Notice that there's no output here. It's not telling me whether or not it worked. But if I run ls or I look in Finder or Windows Explorer, I will notice that there are now GDAL files and Rio files. So I have my RGB files made with GDAL and Raster.io. Now I can visualize them. Now let me go back to the slides. There are a couple different tools that you can use to visualize this data. Like I said, it's not a normal image. You can't view it in your normal image viewer. You have to use specialized tools from the space of Geographic Information Systems, or GIS. There's two really popular GIS tools. The first one is ArcGIS. This is what ARC stands for, if you're curious. It was originally called Info, and then they renamed it to ArcInfo, and then they converted it to lowercase, and then they eventually renamed it to its current name, ArcGIS. ArcGIS is not free. It's a paid service. It's a paid application. But through the university, we have free licenses to use ArcGIS. The problem is ArcGIS only supports Windows, and therefore it's useless to me. So instead, I will be teaching you how to use QGIS, which is free, open source, and available on every operating system you've ever heard of. So any of you can use this for free. This is what I've always used my entire career. I highly recommend learning QGIS. So let me show you how to use this with the example data that we just downloaded. You can, again, once you have QGIS installed, if you've never installed it before, you can go to the QGIS website. You can donate money if you want, but I'm going to skip that. There's two different versions available with QGIS. So there's a long-term version, which is very stable and might not have the fanciest features, but also has the fewest bugs. There's also the state-of-the-art version that has new features, but might have a few bugs. You can choose whichever one you want. It doesn't really matter for this course. We're not going to be using any fancy new features. Maybe the long-term version is safest. You'll notice that it automatically detected that I'm on macOS. If for whatever reason that goes wrong, you can download it for Windows, you can download it for Linux, you can download it for many other operating systems that you've probably never heard of. But for me, I'm going to get it for macOS. The long-term version is probably fine. Regular version's also probably fine. It doesn't matter. This unverified download was blocked by Chrome, so I'm going to download it anyway. This might take a minute to download. The other thing that you might encounter is when you try to install it, on Mac, there's a little .dmg file. On Windows, there's probably a little .exe file. You'll double click this in your Finder or in your Windows Manager, and it may or may not say, this is an unverified download. It's not safe to install it. At least on macOS, you can right-click it and tell it to install anyway, and then it should install, but this is a trusted service. It's available for free. And people have been using this for decades. It's very popular. So this will take a while to download and install, but I already have it installed, so I'll jump immediately to QGIS. Again, if you can't find it, on macOS, you can do Command Space and just search for it by name. There's a similar feature on Windows. Here is what it looks like. When you first run it, it takes a long time to load, but just create a new empty project. There are many different ways to add images to your view. So here is the file browser. This looks just like the Windows Explorer or Finder window. So you can go down through your list from your home directory to your documents, all the way down to whatever location has your data. This is where my Landsat images are. So I can see all of my images here. If I look at band 3, which is the green band, this is what it looks like. You can see it's a black and white image of a glacier. If I zoom in, I can see the individual crevasses of this glacier at 30-meter resolution. So these are very large. But we see a very nice region. These dark pixels are either rock or ocean. These whitish pixels are either snow or ice. This is a grayscale image because we're only looking at how much green is in the image. If we look at those RGB files we created earlier using GDAL or using Raster.io, where's my Raster.io file? If you don't see a file that you think should exist, click this little refresh button, and that will check again. And now I see my Raster.io file. And it should look more or less the same. It should be the same file format. Maybe there's very slight differences in how it was viewed. So you'll notice there's 3 files down on the left here. Let me get rid of this GPS information tab. So there's a browser tab where you can add new files. I think you can also drag and drop files. And this is the currently active layers that I'm viewing on the right. You can see this is the coordinate reference system. It just automatically picked that from the file. That's not too important. These are my coordinates in meters in this coordinate reference system. If you move your cursor around, you can see different locations. By default, you should be in this browser pan map option. This allows you to click and drag and drop your image. You can scroll and zoom in, and this is what our image looks like in RGB. You can see that the ice is kind of bluish, the snow is more white, the rocks are brown, and the water down here is close to black. It's very difficult to see light reflected off of the ocean. I've got 3 different files. I can click these checkboxes and switch between them. You notice that this is our original grayscale image. This is what it looks like from GDAL. This is what it looks like from Raster.io. They're more or less the same. It doesn't really matter. They might handle no data pixels slightly differently, but that's not important for us. If I double click on my file, I can also see more useful metadata. I think it's in a different window maybe. Where is the menu option? It's on my other monitor. Let me bring this over. Oh, it does not want to move. I don't know how to solve this problem. Okay, now it wants to move. You should get a window that pops up like this. This contains many different information. So you have all the metadata from the file, just like we saw from the command line. This can be useful. You can learn more about the source, so you can specify the coordinate reference system here. Symbology is the one that I want to show today, and this is something worth knowing about. So you'll notice that there's 3 different bands here, 1, 2, and 3. If our file was not RGB, if it contained every single band, I could click on this and specify this is the red band, this is the gray band, this is the red band, this is the green band, this is the blue band. But because I made my file in the right order, I don't need to do that. The other thing that you notice here is that it's automatically scaled to min-max, which offers the most contrast in the image, but may or may not represent what the image actually looks like. Especially when there's things like snow or clouds, you might find that most of your image is a little too dark. And if there's a lot of red and not a lot of green or blue, you might end up with an image that gets scaled down where none of the values are very large, even though the ground should look very red or very blue. So I actually recommend rescaling this. I'll put all of my mins to 0, the same values, so it's at the same range. And I'll scale all of these to maybe 50,000 is a little safer. That way the snow is not expanding the range too much. And I can apply. I can hit OK. And this is actually a little bit closer to what it would look like in real life. You'll notice that some of these valleys have shadows cast by these mountains. This is a very mountainous region in Greenland. And I can zoom in to different regions, but this is what snow and rocks usually look like. So if you load your image in this tool and it looks weird, make sure you double click on this and rescale your bands so that it looks like a true RGB image. Okay, that's more or less everything I want to teach you about GIS programs for now. There's a lot of really, really fancy features that you can use these for, but for now, we'll just be keeping it to visualization. I actually want you to learn how to use GDAL or Raster.io to do the pre-processing yourself so that you can understand how QGIS works. QGIS, ArcGIS, all of these tools actually have GDAL as a dependency. And every single fancy thing that your GIS tool can do, you can do from the command line directly with GDAL, and it tends to be faster and more powerful. Okay, so now I will go back to the slides. Okay, I've more or less taught you everything I wanted to about downloading data and visualizing it. So now let's talk about your homework assignment this week. So first off, again, there is a reading list for this lecture. This reading list is relatively short. There are only 3 things this week. I highly, highly recommend reading all of these before you start homework 2, not after. If you read them before, you will save yourself a lot of time with the homework assignment. The first one is for Raster.io. This is a tool that allows you to read and write files in Python by calling out to GDAL with the right commands. So Raster.io is really useful for Raster.io, raster input-output, reading and writing raster images using GDAL. The other tool that we're going to use, just like last week, is scikit-learn. This week we're doing unsupervised learning. We're doing clustering. So it's a little bit different from what you did last week. So I recommend reading this documentation. And in particular, what we're going to be doing is known as image and pixel quantization. And it just so happens that there's a tutorial for this exact same thing. So the images are going to look slightly different, but there is already a tutorial you can follow. Feel free to copy and paste anything from any of these documentation sources or tutorials. Just add a comment saying this is where you got it from if it's more than a couple lines of code. So that's our reading list. What are we doing this week? So we are doing pixel level image quantization. This is a clustering technique, but it's very useful for many different applications. One is image compression. You can actually take an image like the one on the right. This is Guilin in China. You can take this image and you can quantize it where instead of uint8 representation, where you have values from 0 to 2 to the 8th, 0 to 255, you can represent it using a smaller number of colors. So this is a useful application for image compression. You could also use it for land cover mapping. Again, it's unsupervised. We don't know what specific clusters mean, but we can try to look for patterns, look for clusters in the image, and hope that things that are approximately the same color correspond to approximately the same land cover cluster. So imagine this image on the right. If we wanted to use image compression, let's say we only have 2 clusters. Every pixel is either a dark pixel or a light pixel. This is what the image becomes. You can see it's not very useful. Maybe it's a little bit useful if you're trying to separate water and not water, but like water and sky are kind of combined into one cluster. It's not very useful so far. And it really does not look like the original image. So this is only 2 clusters. If we use 4 clusters, now we've got a few different shades in here. None of these shades are actually completely gray. They're different shades of blue, different shades of green, but you can see we're starting to get different colors with only 4 clusters. If we use 8 clusters, we actually start to see different types of fields, rice paddies and things. If we use 16 clusters, now we can see different mountains. Many of these mountains get clustered into the exact same group, but you can start to see actually quite a lot of the image with only 16 values instead of 256 values. If you expand that to 32, it gets even better. And by the time you get to 64 clusters, it almost looks like the original image again. So we've compressed the image down to maybe 16 or 32 colors instead of 256 colors. It's a much more compact representation. So that's what you're going to be doing for your homework assignment this week. I'll show you the Jupyter Notebook in a second. Before I show you that, next week will be the evaluation lecture. I mentioned this in lecture 0. This is the single most important lecture of the entire course. Even if you think that I'm an awful teacher and you hate this course, please come to lecture next week and please learn how to evaluate whether or not a machine learning model is good. This is extremely useful regardless of whether you use machine learning models to understand how people can tell you, look, I've got this amazing model. It's the best model ever created. All you need to do is ask them, how well does it work? And if they know what they're doing, they should be able to show you evaluation results and tell you, mathematically speaking, how good is this model? So this is a really important lecture. Please come, bring your friends. I will teach you all about evaluation next week. But first, let us cover the homework assignment. So I have it open here. It will be available on Moodle, just like always. We are doing both downloading and visualizing satellite imagery, as well as unsupervised machine learning on this imagery. I'll zoom in a little bit. These are the same bullet points as always. Upload your Jupyter Notebook as a .ipynb file. That way it allows me to actually run your code. It's not just a PDF. Also, run your code and save the output so I can see the plots that you make, so I don't have to rerun it if I don't happen to have the exact same file running around. There are a couple steps in this homework assignment that require you to include a screenshot. This turned out to be the hardest thing in the entire homework assignment last year. Very few students figured out how to do it. Here is a website that shows you how to do it. I recommend the first approach, where you drag and drop your image into the Jupyter Notebook into a markdown cell. A lot of people last year did approach 3, where they actually hard-coded the path to the file on their computer. The problem is I'm not on their computer and I don't have their file, so this won't work. If you are concerned, as a backup, you can also upload the screenshot files that you take, or even upload a PDF file from your Jupyter Notebook. You can always hit File, I don't know if it's export or yes, save and export notebook as PDF. That's also fine. You can upload a PDF, but also always upload this file. This lets me run your code. This is the thing I'm most likely going to grade. So that's the usual. It's due in 2 weeks, right before class starts. Again, if you need an extension, let me know before the deadline, not after. And those should be used sparingly if you're sick or you didn't have time to finish it because of some extenuating circumstances. Don't ask for an extension every week. As long as no one abuses the system, I'm happy to give an extension anytime you actually need it. So what are we doing? We're doing pixel quantization, just like we talked about in the lecture slides. Here's an example with 16 clusters. But we are going to be doing this on a satellite image. Again, you can use this for lossy image compression. This is how some image compression algorithms work to make your images smaller, not specifically ones like JPEG. Those use a different method that we won't cover in this course, but this is one form of image compression. It can also be used to cluster pixels that look similar. So ideally, if things look similar, they're hopefully similar in terms of meaning. So 2 pixels that are both forest should be approximately the same color. 2 pixels that are water should be approximately the same color. This is not always true, and we don't really know what each cluster means, but we can still use this as an unsupervised form of classification. So what are we doing on the homework assignment? Again, just like the last assignment, the first thing is imports. You don't get any points for this. These are the things that you are allowed to use. If you import something that is not in this list, you will lose points, so don't do that. But you can use anything in INOPS, anything in Matplotlib, anything in NumPy, anything in Raster.io, and anything in scikit-learn. That's completely fine. Even if I don't import a specific function from INOPS, you can import other stuff from INOPS, I don't care, but don't import PyTorch or SciPy or some other library. These are the libraries that I want you to learn and use for this homework assignment. Also, these are the imports that I used to solve the assignment. So, hint, hint, you should really read the documentation for these things and know what they're for, know what they do. Otherwise, you might waste a lot of time reinventing the wheel when there's a convenient function that does exactly what you want for you. So what are we doing on the homework assignment? There's several steps. The first step is to download a Landsat 9 surface reflectance product with less than 20% cloud cover, covering an interesting or diverse region. Guess what? We've already done this during this lecture. So if you were following along, you've already done step 1. You've already gotten 10 points. Congratulations. I want you to include a screenshot of the website that you used. Hint, hint, this may or may not be the name of the website. So have a screenshot of like the entire window so I can see the search options, not only the part that you downloaded from. So I see proof that You did indeed use the right website. Step 2, pre-processing. Combine all the different spectral bands, specifically the ones for red, green, and blue, into a single file. This can be done using raster.io directly in Python in 10 or 15 lines of code, or it can be done using GDAL or Rio from the command line. Guess what? We've already done this too. Congratulations, you've got 20 points so far. If you do this in raster.io in Python, just write your code in this cell. If you do it from the command line, I still want to know what code you ran. Hint, hint, rewind the video to see it. But put the answer in here with your actual file names. And if you start with this command, you can actually run things like GDAL merge from the command line in your Jupyter Notebook. So that's what the exclamation mark means in a Jupyter Notebook. And then the third step, display this image in true color RGB using GIS software such as QGIS. Congratulations, you've already done that too. So you've already done a third of the homework just by following along with the lecture. Include a screenshot of the entire window. So again, this whole thing, not just the right panel, so I can see what your files look like and basically prove that you use QGIS. You didn't just plot it in something like Matplotlib. Again, for including screenshots, try to drag and drop the image into this markdown cell, or if you're not sure if it worked, you can also try to upload both files or upload a PDF in addition to the Jupyter Notebook. Okay, so what haven't you done yet? What else? The first thing we want to do is load our image in Python. Like I mentioned in lecture, raster.io is the library for loading images, so we're going to use raster.io to do this. If you read the reading list for this week, there is a documentation page that tells you exactly how to do this. Now, if you remember, the image that we downloaded was like 9,000 by 9,000 pixels. It's a gigantic file. It's around 1 or 2 gigabytes in size. If we train a model on the entire image, it will work, but it will take a very long time. So what I want you to instead is to use a smaller image, about 1,000 by 1,000 pixels, 1,024 by 1,024 pixels. You can get this from the center of the image where there's no data pixels. So if I zoom out here, you'll notice that the image is rotated because the satellite is moving at an angle with respect to the Earth as the Earth spins. So the entire image looks like this. Pick a location like maybe here that's kind of interesting and doesn't have any no data pixels around the side. There's two different ways to do this. The easy way is to load your image using raster.io, and the resulting image will be a NumPy array. And if you know a little bit of NumPy, you can use NumPy slicing and indexing to chop your image down to a smaller size. This works. It's very easy and simple, but it's kind of slow because you still have to load the entire image into memory, and it takes a little while to load the image. What you can do instead is raster.io has a fancy feature called windowed reading, where you can specify the bounding box of the image that you want to load, and it will only load that part of the file, and it's much faster. It doesn't matter what you use as long as you get a small image that's small enough to quickly load and quickly run for later steps. Now, a really important hint here, unfortunately, all of these different software libraries load and process and visualize images in different formats. So raster.io and also PyTorch, which we'll be using towards the end of the course, both use images in the channel height width order. The next thing I want you to do is plot your image. And in Matplotlib, every image has to be in height by width by channel order. If you are not careful, it is really easy to make a mistake here. Again, there's a couple different ways to do this, to change the order of the dimensions in your NumPy array. One is directly with NumPy. There are NumPy tools that make this easy. and you can use any one you want. Hint, hint, this one might be useful. This one might be even more useful. You can also use a tool called einops. And I really, really like einops for this purpose because instead of saying swap axes 0 and 2, you can say, I want to go from CHW to HWC. And all of a sudden your dimensions have names, and it is much more easy and intuitive to think about how you are rearranging the different axes or dimensions of your array. So for matplotlib, you have to reshape it to this shape. The other thing that you will notice is if you just plot your image in its original format, which is uint 16, 0, any value from the range of 0 to 2 to the 16, your image is probably going to look black. And matplotlib will issue a warning saying your data is out of range. If you are plotting images in matplotlib, they either need to be integers from 0 to 255 or floating point numbers from 0 to 1. You have to convert your image to the right data type and to the right range in order to plot it. Hint division works well here. Now, finally, after all of this downloading, visualizing, pre-processing, we get to do some machine learning. We are doing clustering, and we are specifically doing k-means like we learned about in lecture last week. You're going to want to experiment with many different values of k. Remember, k is a hyperparameter. You have to choose that first, and then you can train a model, learn the right parameters, learn the right centroids and exemplar values in order to use it. And again, scikit-learn requires your data to be in a new format. You need to merge the height and width dimensions into one dimension. So you end up with a really long matrix. So it'll be about 1 million pixels long. You'll have 1 million rows, but you'll only have 3 columns. So in this case, you have 1 million examples, 1 million pixels, and you have 3 features, red, green, and blue. And you are looking for patterns in that RGB space among those 1 million pixels in your original image. So this step is the scikit-learn step. This is where you do your k-means. Again, please read the documentation for k-means. It tells you exactly how to access the centroids and exemplars and all the other things you might need to use. Okay, so now that we've done our clustering and we've tried many different values of k, how do we choose the optimal value of k? Again, if you remember back to lecture last week, I taught you a method for finding the optimal value of k. Look back through the lecture slides if you don't remember what it's called, but it's not based on what the image looks like. It's not based on intuition. There's a specific method where you create a plot. One axis is the sum of the squared error. The other axis is k. Using this plot and a specific method I taught you last week, determine the ideal value of k and add a little mark on the plot, such as like a point labeling what your ideal value of k is. Then, once you've found the ideal k, use those k cluster centroids. These are the exemplars we learned, the average color. Use those to replace the values in the original image. So every pixel in your image, all 1 million pixels, should belong to a specific cluster. Replace that cluster value with the centroid color and plot the resulting image in matplotlib. If your image does not end up looking something like this, where you can see there are certain things that are mostly the same color, there's certain places where it looks a little bit blocky, but it more or less looks like the original image, just a compressed version. If that's not the case, you probably did something wrong. So that is what it should kind of look like. For extra credit, there's another style of image quantization where you can actually do it at the patch level instead of at the pixel level. So here, instead of every data point being a single pixel, so instead of having a input thing that is 1 million pixels long and 3 features, now an entire patch, a P by P patch, becomes our feature. One of these little image patches is an entire input into our clustering algorithm. So for extra credit, do this exact same thing, but for patch quantization. Specifically, these are the steps that you need to do for extra credit. First, download a Sentinel-2 surface product with maybe the same location, maybe not. Maybe it's your hometown, maybe it's an interesting place that you found on Google Maps. It doesn't really matter where the image is from, as long as it looks kind of neat. You've already done this. So if you add a screenshot showing me how you downloaded a Sentinel-2 image on a certain website, hint, hint, you've already gotten partial credit for the extra credit. Load the image in Python. You've already done that too, so that should be easy to copy and paste. Now this is where it gets a little trickier. You have to chop up your image to a bunch of smaller image patches, each 32 by 32 pixels. Reshape those images to this new dimension. Now I want you to perform hierarchical clustering, hint, hint. Read the documentation for this function, that might be useful. Do hierarchical clustering on the image patches instead of k-means. Next, create a dendrogram plot of these clusters. Hint, there might be something built in that makes this very easy. And then using 32 exemplars, I'm telling you which k to use. Your k is 32 and your patch size is 32. Replace each patch in the original image with its cluster centroid. If it does not look something like this, again, you did something wrong. And then plot the resulting image in true color. When you're making these true color plots, if I look at the image and it's all black, you're not going to get full points for that. But in general, for all of these steps, there's usually some partial credit. If you make minor mistakes here and there, don't worry about your grade too much. So this is the extra credit. It's a little bit harder than the extra credit the week before. But again, even if you only do parts of the extra credit, you still get points for that. So that's an easy way to make up for points that you might lose in earlier parts of this assignment or other assignments. Again, it's extra credit. It's completely optional, but it might help boost your grade. So if you have any questions on this homework assignment or on homework 1, which is due in 1 week, feel free to email me. I'll try to answer your email while I'm on vacation. I won't leave you hanging. I hope you enjoyed this lecture as much as I enjoyed the beaches of Santorini and volcanoes and hot springs and things. But enjoy your week in Munich. It looks like the weather is finally warm again. So it's actually a similar temperature during the day in both Munich and Santorini. So thank you for attending this lecture, and I will see you when I'm back next week.